Hi again. Welcome back. Give yourself a little time here. Oh, I just realized that I still had my AirPods in, so you may not have even been able to hear that. I'm sorry. Maybe just the pretty dripping water was kind of calming. Okay, so in my notes, like I said, I wrestled with this. What was the point? What did I want to get across to you? And so in my notes, I labeled this selection coefficient. So what? Why do we care? And I love that many of you are asking me in our small team meetings, why does it matter? Why do we care? Why is this important? That's a great question. And I hope you always ask that. So why do we care? What is the selection coefficient? What does it do? Why is it important? And I'm going to show you this with math. And then what I'm going to work on tomorrow and over the weekend is coding a simulation for you to play with so that you can actually visually see how these different things influence what's going on in a population, what's going on with positive selection. So what? What do we care? Why do we care about the selection coefficient? So gonna play with probabilities here. So let's say that P equals the frequency of A2 in a population. So this is the frequency that's already there in a population. And let's imagine we're interested in positive selection, right? We're interested in the possibility of a selective sweep. And so in the case of a selective sweep, you have a newly introduced allele or a allele that starts at very low frequencies, maybe been hanging out at very low frequency, and then it sweeps through the population. So we have positive selection. And so what we're gonna say for A2 is that our starting frequency, we're gonna make it low. Okay, so in the case of a selective sweep, we're gonna start off with a low frequency. And we're gonna make, do I wanna do that? Yeah, so hang on just a second. I'm gonna fix this. Okay, evidently I'm still sorting through this. So P is the frequency of A2 in a population, and we're gonna set this low. So we're gonna imagine that this is a relatively new allele, maybe a newly introduced allele. And then so to figure out how is A2 going to change in this population from generation to generation, because remember, evolution occurs across generations. And so we want to figure out how is the frequency of A2 going to change in this population? So we have a formula for that. I know you're surprised. So this is delta P, and the delta means change in. So change in this allele frequency. And we're interested in A2. This is our focus. And what the formula is equals S, so that's our selection coefficient, times P, okay, P up here, frequency of A2, times 1 minus P. I don't know about you guys, but these formulas always make my head hurt a little bit. So let's break it down. Okay, so P, we said already, equals 0.1, right? So P equals 0.1. And then in our formula, we're going to multiply that times 1 minus P. So 1 minus P, if we take 1 and we subtract P, we get, okay, that's starting to look a little bit familiar. What if we add, what do we get? 1. So let's simplify this a little bit. S, where did I write this? Change in P equals S times PQ. That Q should already be familiar from our discussions on Hardy-Weinberg equilibrium, I hope. Okay, so now we've just kind of made this a little bit simpler. Hopefully all of this is making sense so far. So P and Q, these are just the frequencies of the different alleles. If the frequency of one allele is 0.1, the frequency of the other allele has to be 0.9, right? P plus Q has to equal 1. So the change in P equals the selection coefficient times PQ. So why are we multiplying the selection coefficient times PQ? PQ is a measure of the genetic variation. And we're going to come back to that in a minute. Okay, so we've kind of set up our equation. We've figured out our numbers. So now let's just take this PQ, simplify it further. So P equals what? 0.1. Q equals 0.9. So PQ equals 0.1 times 0.9. So we can just substitute now this number, 0.09. Okay, so S times, so now what we've done is we've said, all right, our genetic variation is 0.09 in this population. Cool. Now we're going to get to the whole selection coefficient. What? Like, why does this matter? So this 0.09, this is going to stay constant right now. This is going to stay the same. And what we're going to do is we're going to play with the selection coefficient and we're going to see what that does. The whole point of that is to help you hopefully conceptually understand what this means, okay? So we're keeping our genetic variation the same. We're keeping our frequency of our P allele and our Q allele the same, and we're just going to play with S. So we take S, let's make S, and remember I said a selection coefficient of 0.1 is really high. So let's set S equal to a couple of different options. So let's set S equal to 0.01 and see what happens. Let's set S equal to 0.02, and then let's set S equal to 0.05. Okay, different intensities of selection. And in every case, we're going to use the same genetic variation. So we're going to use the same allele frequencies. That's going to stay the same in every case. Okay, so in every case, we're multiplying this number Okay, so what I'd like you to do now is just multiply that out real quick. Just take a second. Figure out what those numbers are going to be. Okay, here we've got big, lots of decimals, right? But the take-home message is that if selection is stronger, right here, that number's bigger. If we have stronger selection, then remember what we're solving for here is the change in P. So the change in that A2 allele, this number is bigger if we have stronger selection. Okay, we've got a bigger, is that showing up? Yeah, we've got a bigger change in P. We've got a bigger change in the A2 allele if we have stronger selection. And so I'm showing you that here with numbers. And this is from one generation to the next generation. So if we have a selection coefficient of 0.01 and we're holding our allele frequencies the same, what we're doing here, so our original P allele frequency is 0.1, right? So every generation for an S of 0.01, we're taking that 0.1, which was our original frequency, and we're adding 0.0009 to the frequency. The frequency, so that means how frequently does that allele occur in the population? Here we're doing, okay, you get it. You get the point. Okay, so this is every generation. So then this is cumulative, okay? So the next generation, that 0.1 is going to be 0.10009. So that's going to be our starting point in our genetic variation portion of the equation. So that's going to be our starting P. If our selection coefficient is 0.02, our starting point for the next generation is going to be 0.10018. So we're starting with a higher frequency, okay? So what does that mean? Why do we care? Okay. So what that means and why do we care is how frequently is this allele going to become prevalent in the population or maybe even fixed in the population. So how strong is selection is going to influence how rapidly this allele increases in frequency. So if selection is 0.01, our lowest number, then if we're just like looking at an imaginary plot, this number is going to come up real slow, right? Okay. If it's 0.02, it's going to come up faster. Okay. And as you're probably guessing, if it's 0.05, it's going to come up much faster. The frequency of A2 allele in the population. So how frequently this allele increases in the population depends on the strength of selection. And that's what all these numbers mean, okay? Depends on the strength of the selection. Not only does it depend on the strength of selection, though, it also depends on the original allele frequencies, right? So what I'd like you to do is take an S of 0.02. So keep your S, hold that constant. So this is going to stay constant. And play with your allele frequencies. So your allele frequencies in this equation, so we've got S. Our S is going to stay 0.02. Then the other part of this equation is that P and Q, right? So play with what happens if you change the P to 0.2, to 0.3, to 0.4. What does that produce in this number, in the frequency of P? What numbers do you get? What does that do? And then do that 2 or 3 times, 2 or 3 different allele frequencies. And then plot it. The plot doesn't have to be perfect. It can be relative. So plot, if we start with a different allele frequency, how does that influence the frequency of P? Okay. So that will be your blog post for this lecture, is playing with that, showing what everything is. Make sure you label everything and all of that. And then on Monday, we'll come back and hopefully I'll have a simulation for you to play.